Hello, once again. Welcome back to me following failure of my experiment. Although I've got a third experiment going, I'm trying another method that is something that doesn't interfere with my regular stuff. I can record videos. First thing, if you've been looking at the information material I provided. Somebody said something. And hopefully the title of this video, I want to demonstrate for you the fact that in user mode, the user mode Win32 programs use what's called a flat memory model. And what that means is that, as described here, we have a single address space for 4 gigabytes. You can't use all those gigabytes, but the address space, the range is from 0 to the 32 minus 1. So an address, an address lookup can be done by using any valid segment and giving a 32-bit offset. Where that winds up with physical memory is none of our business. But we can view the entire thing as just one contiguous chunk. The segmented model is different in that depending on which segment is being selected for an address lookup, we may get a different value. Okay, but I'm asserting that we're using a flat model, and I'm going to prove it. The first thing I need to do that is some kind of variable I've defined here. Some address that I know I can look up without causing a crash. Okay, so I've defined a static int variable with this value. Okay, so it's easy to recognize. Now I've used the compiler to obtain the address of that variable. Okay, now this can be done in assembly too, and I'll show you how that's done in a minute, and why this naming is. I could add some more to this name to be more explicit about what this is. Okay, now these comments go on all of these. Same comment. What I've done here is I've taken that. Now, one thing I can't do, right? You would think that I could just say move into EAX var or something, right? But I can't. If I did, and I can't do it this way either. If I do this, I'm going to get the value 1, 2, 3, 4, A, B, C, D. If I do this, I'm going to also get that. It's the inline assembly. It automatically dereferences these C values. And so you can't, in the inline assembler, use a move instruction to get the address of a variable. You notice that? Okay, I'm just going to show you that this here is going to give me that. Okay, now I'll step over it. Here's what I got into EAX. That's not the address of var or anything. What I want to put into EAX is this value. But what I've done here is I've used the compiler's knowledge as it's building the program to take that value and store it into another variable, which I can always get the value of a variable. Okay, no matter how it does that computation. In fact, when I put this not on the stack, so there's no confusion. And we should find that this value, address of var, is the address of this thing is var plus 4. But I don't know how to do that. So this is what I want in EAX, and it's exactly the equivalent of that. I can put both. One in BF, AX, and one in BX. See if they're the same. But essentially, I need to, in order to do this test, I need to get a memory address that at least by default I can look up. Okay, now I'll run up to here. Now, I don't think it'll show it won't show the other calculation because that was part of the loading routine. However, you will note that although this instruction appears longer, it is longer. The disassembly of the human readable form is the same. I don't know why this is larger, probably because BX is not the usual or something. So AX is the number I wanted, and BX is identical. Why these are different length instructions is anyone's guess. Alright, before proceeding, I've shown you that these two are the same. Oh, maybe the brackets. I don't know. Let's try with this one. I'm curious. But the brackets shouldn't, in Microsoft's inline assembly, bracket variable is the same as variable. So but I don't think I could try it. I don't think you can do this without the bracket. Alright. But here again, I'm pretty sure it's just BX. It's the use of BX. Yeah, see, it's the same. BX, I guess, well, I don't know why BX is considered differently. AX is, that's an 8B, that's the same 8B as this. And that refers to this instruction. And then these ones are longer. Oh, because that's something else. Alright. Now I just want to show you one more thing. I can get rid of address var, and I can do it in the inline assembler using a special instruction. This instruction, LEA, LEA stands for load effective address. Okay, I probably don't even need these brackets. And basically all that does is it gives me the address of the thing referred to in the brackets, right? Now the compiler is going to turn the thing in brackets into that number for something, something, something. So this just has the effect of moving the actual address into AX. It essentially strips the brackets. Okay, ready to go. Now what you're going to see here when I show you what this amounts to in assembler, it's supposed to be assembler. It is LEA into EX. Now it's using the default segment for that particular variable that I referred to, or for anything, right? The default is DS data. Okay. Now that's the number I wanted. Now it's not saying move, right? If it was moved, then this would be a dereference. There's no dereference. All it gives me, this instruction will give me, is what's inside the brackets. And there it is. See? So in the inline assembly, I can actually compute the address of var, and I have an address I can read from, at least. But I still want that address of var later on. Okay. So, yeah. All right then, here we go. I'm just, oh yeah. Oh no, I have it. Now the first test, for the first test, something there. What I want to do is put into CX just bracket AX. Now the default, if you just use brackets on their own, is the D is using D. We'll use DS here, which is 23, as the segment. Okay, and what I got is the correct answer: A, B, C, D. Okay. Now, is that easier to read than this? No. Well, we gotta see that it actually did what I asked. Now, the next one is specifying specific, not using any default. I'm saying I want DS EAX. Now, I don't know if I've shown you segment override. I know I have shown you how the segments and how addresses are computed in real mode using these segments, but these instructions aren't usable in the 16-bit land, but you can still do it as part of an instruction. You can prefix an instruction by something like ES colon, which is like changing drive. Let me give you an example. First, let's look at our registers. Now, I've been playing with this, and it keeps retaining everything. mess up the memory a bit. Okay. Now, some memory. We can see here that currently our instruction is waiting to be executed is at position 144, 100. All right. What I'm going to do is I'm going to put an instruction in there to. What I want to do is get the byte at position 188. Move a low. It has to be a byte value. Now this should work. Why? There's several reasons why it should work. And it's showing us, in fact, in the disassembly, that at position 188 should be 5E. That's correct. But it's also showing us that what the default is. DS. Okay. Same in 32-bit mode. However, I can change that. If I want to use a different register instead of DS, I can change it like this. First, you can imagine these segments as like, this is my D drive, this is my E drive, S and C and so on. And if in that view, I could select a different drive, like, changing drives. Now you'll notice that it treats this as one single instruction. And that's exactly what we have here, except I use DS. And I have no specifier for the size. But it's showing us that ES188 is 5E. Now, you don't believe that it's using that. Well, we can run it, but first let's change ES. I'll add 1. Okay, now the same instruction is showing a different result. We're going to get a different result in A level, namely 1C, because I added 1 to the ES, which adds 10 to its offset. In real mode, how you calculate offsets. You take the segment value times 10 and so on, plus offset. So if I wanted to get the same value through ES, I would have to subtract 10 from the offset. Okay, and that would give me the same value. So ES178 is the same as DS188. Now, when all of those values were the same, it wouldn't have mattered. It doesn't matter which one I choose, and that's called a flat memory model. So now, into CX, I want to put DSAX, and obviously that's going to be the same. Okay, so now CX, you can see, didn't change, and I'm storing that variable into that value CX that I just computed into what I called value at DS address. Now I'm going to choose the ES segment with the same offset. Okay, now you can see ES is ES. It's the same as DS, it's 23, so you don't expect any difference, no difference. Now SS. SS is to be 23, so we shouldn't expect any change there. And now, but CS is different. It has a different segment value. Okay, I'm using the CS override here, but again, CX didn't change. So the result, printing it all out, is that for every register, DS, ES, SS, and CS, if we get anything, the four main segments for that address, and it's true for every address, we get the same value. That is, it's a flat memory space. All the segments are aligned together. Now, what about this FS? Well, you can probably guess what's going to happen here. Here I've done the same thing. I reload AX with that value. I have GS. GS is 0, so we expect a crash. And we get a crash. And we'll get a crash with FS, turns out. But FS is not used in regular in your regular code. It's special, and so okay, it's nearly flat. Anything you put into brackets is going to give you the same value, and so that's why it makes sense to store, for instance, the address of a thing on the stack and be able to use that address in the same way that you would use any other address, because stack addresses are based in the same way as data, and similarly for code. A code address is in the same range, or an offset in the code segment is the same offset as in the data segment, but it has different attributes. I'll show you that this will crash, even though FS is valid. It happens to be not overlapping, and we've seen before, because FS0 is valid. This here is not going to be valid. And you'll notice that the location always comes back with -1. And now there's a reason why it comes back -1, but we don't need that. So that's why, if you wanted to, you could call this the effective address. If you wanted. That's the normal lingo. I think that's the only place I use that. The normal lingo in the assembly world, we talk about effective addresses. And that makes sense when you read it this way. Right? Load the effective address of var into, put that in order. Doesn't matter. The effective address I do use that here, don't I? Also known as the linear address, is the offset part of an address in a similar sense as what appears in the square. It's what appears in the square bracket. Now the actual address calculation from the effective address to physical address is something that the operating system deals with in its own way. However, I've shown that we can read the values, and all the values came out the same, but unfortunately there's not very much mix-up here. The only one we expected might be different was the last one, but it wasn't. It was the same. Okay. Therefore, that proves that we're using a flat memory model. So, when you put something in square brackets, it doesn't matter what register you're talking about. It could be stack, it could be whatever. You're going to get the same value. Here's an interesting, oh, I fixed it. Here's an interesting thing. Now, suppose instead of this bar, or instead of putting bar here, I put the bar on the stack. Okay, I can do that. Now, let me stop this. Now, one thing you may have noticed, especially when you're for these console programs, is that stack addresses, this is a linear address, are small, and below the address, we should put 2, right? Below our current address is 6 digits starting with 4, and this has 6 digits starting with 1, right? Now the claim, so therefore the stack is below the program, right? What if let me just run through the thing again, make sure everything's still the same. Should be. Okay, everything worked out the same. CS colon that, right, gave us that. One of the things you're allowed to do is make the stack. We're given 4 gigabytes of address space. What if I want a stack that's so big that it wouldn't fit underneath the program? Well, I can do that by increasing my stack size. You can ask to reserve a stack size as big as you like, less than 4 gigs. So that's 1,000. That's 1,000,000. So that's 100 million. 1, 2, 3, 100 million. I've asked for a stack size of 100 million. I don't know if this is. Okay, in hex, that's this value. That's more than our position in memory. So where do you think it's going to put the stack? Well, it can't be what it was before. Let's find out where it goes. It definitely cannot be, a 6-digit value starting with 1, because there wouldn't be enough space from 0 without colliding into our program. And here's where I put the stack. Okay, disregarding that. So the stack now is at this address, which I don't know if that'll convert to decimal. $640FF00. That's curiously 100 million, right? 100 million plus 492280, which is essentially the size of our program. So it went 100 million above the position of the program, so it exactly fits Yeah, the stack. We have the stack, and here's our program. I don't know the size of our program, but I think it's in the 4.6. We're already at 4.6 something, right? Or sorry, 4.6. What was the value? 4.9. I don't know. I can check. So program code, utext. We can find out the size of the program in memory, but rest assured it'll have a. I asked for 100 million bytes. I get 100 million bytes. It's too bad I can't specify. Maybe I can put hex. It's quite a lot, isn't it? Notepad. My notepad's not very fast. It's long pastes. Yeah. There it is. Let's just see. Base image size of image is AE000. So the total program image size should be 4EA. 4AE. 4AE. And 1 million. Oh, but this is decimal. So what's 4AE? Or this? AE. 44544. So it's definitely more than enough, right? There's also other stuff. Like that's the size. I'm not sure if that's the total size. Well, it might be. Yeah, it'll get there. My search is slow. Come on, you can find it. I don't know why it's so slow. Who am I using? I'm using my here. This is what I'm looking for. A5. It's okay. Bigger than that. How much is this? See, there are different things. Data and code. 676. Definitely still less than the number, I think. 4 here. 487 in decimal. 4 million. But this is nearly 4 million, 5 million. It looks exact, in fact. So there you go. So step A, we're done showing that the model is flat. Things in square brackets don't need any overrides or anything. It's a simple 0 to 4 gig address space, except for FS, which is the segment that we're actually most interested in. However, I showed you before. I don't know, I don't have it here in that document. At FS18, we can get the linear address. I don't think I need this, but I'll put it in anyway. This gives us the linear address of the start of FS0. So bracket of EAX after this instruction would work. I had a variable for it, so it's not the right wording. Now that gives me an address. So what I need first is this gives me the value at that address. I don't think I can put the two things. No, I definitely can. This will give me what's at FS18, and it should be the same as FS0. Okay, so FS18 gives us a linear address of this great big value, and now I'm taking dereference that into dx, and that gives me this value, which is something on the stack, you'll notice. And save that off, but I haven't printed it out. But there it is. It's on the stack because it's in that same range as where our great big stack is. Okay, all right. So we'll leave that there.